All right, so taking a look at example 2. As we look at example 2, take a look at how strange this next series is. Not every series we have will converge. They'll say find the first partial sum for this sigma, and you've got -1 up to the n minus 1. Hey, if I plug in a 1, guys, I'll have -1 to the 1 minus 1. 1 minus 1 is 0. What's -1 to the 0 power? 1. And then you'd say, well, now do s sub 2. Well, technically, you're saying take your first term, which is this, add it to the second term right here. And we already saw our first term, -1 to the n minus 1, or 1 minus 1 was a 1. How about this second one right here? -1 to the 1 is -1. So we saw the first part was a 1. Then this is -1. You'd be like, oh, would you look at that? You add up to 0. And then you could say, well, what about s sub 3? Well, again, what's happening is, if you're adding up these first 3 terms, you already know that these two wiped out to 0. You just saw that in the previous work. 3 minus 1 is 2. -1 squared is back to a 1. Oh, so look at this. My first partial sum is 1. My second partial sum is 0. My third partial sum is 1. You might say, well, what about my fourth one? Well, you might have a pretty good guess right now what that is. You would already know that, hey, the first 3 terms, hey, I worked that thing out. I worked all that out. This thing, all of this should work out to a 1. And this is -1 to the third. That adds up to -1. This thing works out to a 0. Now, do you think we're dealing with partial fractions here? Well, of course not. Partial sum. It sure looks like we're going between what 2 numbers? 1 or 0. Looks like we're going to be at a 1 if what happens? If n is odd. And we're at 0 if n is even. So here we are. We've got this, going between a 1 and a 0 right here. Show that s of n is going to diverge. Well, wow, what you've got is the limit as n goes to infinity of s sub n. Very clearly, that does not exist. Right? As you're going off towards infinity, you are oscillating between a 1 and a 0 every time. You're never getting within that bandwidth that we were talking about the other day. You're never saying, ooh, I'm getting closer and closer and closer to that real number. So if you're bouncing around between any 2 values, guys, that's going to definitely diverge. Well, for example 3, oh, wow, put some stars right here. This is the harmonic series. The harmonic series is one of the most famous series that you're ever going to study. There will come a point in this unit when we are going to refer to the harmonic series on a daily basis. We really will. We'll be using it in comparison methods. And we're going to be able to say for a statement of fact that the harmonic series diverges. It might not look that way. I'd like to show you a little quasi-proof right now to show you that it does. Let's look at this. If I gave you 1 over n, and we're going from 1 to infinity, let's start writing out that sum. First term is a 1. Then I'd get a half. Then I'd get a third. Then I'd get a fourth. Then I'd get a fifth. Then I'd get a 6th, and then a 7th, and then an 8th, and so forth. ... You get the idea. And I'm going to make a bold statement right now. This diverges. Right now, you might not think that way. What I'd like for us to do is to take a look at another series. I'm going to say consider this series, T sub n, and I'm just writing, some other kind of a pattern in there, where I'm going to write things that look like they're almost identical to the harmonic series. But you're going to see I'm going to group some things together in the harmonic series. Here's, I guess, what I want to ask you. What's bigger, 1/3 or 1/4? 1/3 clearly is bigger, isn't it? What if instead I chose to come up with a crazy summation where I said, you know what, rather than have the 1/3 there, I want to turn that into a 1/4. And what if for the next pattern over here, looking at an 8 here, what if each one of these I wanted to replace with a 1/8? By the way, then, next one we would be choosing appropriately. You might wonder if we're dealing with powers of 2. 2 to the first, 2 to the second, 2 to the third, and so forth. Yeah, we could think of it that way. But I guess what I'm trying to get you to see is I could create such an addition. I could sum something like that up forever. Let me ask you this. What's 1/4 plus 1/4? It's really 2/4, which is a half. Hey, what's 1/8 plus 1/8 plus 1/8 plus 1/8? It's 4/8, which is actually 1/2. So what if I decide to just add everything up like this forever and ever and ever? So I said add 1, but then you keep adding 0.5, 0.5, 0.5 forever. Do you think you're going to level off to something like 1/3 or some fixed value? Now, would you agree you're going to head off towards infinity, albeit very slowly? Right? Just keep adding that. So we can say that this series right here, T sub n, diverges. You can say it's actually going to approach infinity. But this thing right here, if you really think about it, right now, this T sub n is actually, what do you think? Is it going to be bigger or smaller than the harmonic series? Well, here's my point. Let's start doing some comparisons. Where did we start deviating? Did we say 1/4 right here? That's difference. That's actually smaller, isn't it? And then you look at this 1/8. Is 1/8 bigger or smaller than the 1/5? It's actually smaller. And this 1/8 is smaller than the 1/6. And this 1/8 is smaller than the 1/7. So I can say with certainty right now that this series is smaller than the harmonic series. I'm adding up smaller numbers. So if I'm taking a smaller sum and it's launching off towards infinity, what do you think the bigger sum's going towards? To infinity as well. So you could say, so this series diverges also. Now this is a little quasi-proof to show that the harmonic series actually diverges. We're going to use that as a statement of fact. You're not going to actually have to prove it this way. We're going to learn some other ways that you can show it. All right, real quickly, the geometric series. Oh, wow. You can see I've put 3 blue stars off to the side. You're going to have geometric series a lot. You're having this lesson today. You're introduced to the harmonic series, a super, super popular series you're going to see for the rest of this unit. Geometric series we're going to use extensively. Geometric series, look, each successive term has been multiplied by a common ratio r. A common ratio r. Geometric series, guys, what you're going to see is each term gets multiplied by some constant called a common ratio, called an r. And look at this. You can say, well, wow, if I'm going to add all this up forever, We're going to say a geometric series converges if the common ratio, that R value, is less than 1 in absolute value. The formula to find what it adds up to is the first term, a sub 1, divided by 1 minus the common ratio. By way of comparison, if your common ratio is equal to 1 or greater than 1 in absolute value, then you will diverge. So, let's take a quick look right here. You're going to see so many problems like this. First question is it geometric? And I think that's the big question. So going from 4/3 to 4/9, what kind of math does it look like we did? Multiplied by 1/3. Do we continually do that to get successive terms? Yeah. So what we're seeing is R would equal 1/3. And my first term, what's that? It would be 4/3. Right? Notice it's the first term of a sequence here that I'm actually writing out. But do you think this series, if I kept adding up forever, do you think we'd add up towards infinity? Or do you think we're going to converge? We're going to converge. Here's why. R is less than 1, so we are going to arrive at a convergent sum here. We're going to take our first term, which is 4/3. We're going to say 1 minus 1/3. 4/3, 1 minus 1/3 is 2/3. Hey, you can divide out the 3's. 4 divided by 2 is a 2. Hey, you keep adding that up. After a while, you're going to be like, wow, this is interesting. I'm getting close to 2. Continue to add it up. I'm getting closer to 2. Sure enough, eventually you would arrive at 2 as you proceed towards infinity. But the limit idea means, of course, we're not going to get there. It's what if we could go on forever. You'll get close enough to that 2. All right. By the way, if R would have been bigger than 1, that's when you just say you diverge. Okay, so super helpful stuff here. Here's a theorem that's super important, but in all truth, we don't use this form as much. If a series is convergent, then the limit as n goes to infinity of its nth term in the sequence equals 0. Now, we don't really use that as much, but we use a contrapositive of that. You guys remember the contrapositive back in geometry? If you had a statement P implies Q, what's the contrapositive of it? You guys remember? What? Not Q implies not P. And you actually can use that in logic courses like philosophy and all. It goes beyond math. If a statement is true, its contrapositive must be true also. Wonderful. So if this theorem is true, here's my P. If a series is convergent, call that P, then the limit goes to 0. So guess what the contrapositive is? It's right here. If not Q, and this is the one we use a ton. Oh my gosh, this becomes your lifeline. It's going to be known as the nth term test for divergence. Wonderful, powerful tool. You're saying if not Q, if the limit of the nth term as n goes to infinity is not 0, then the original series does not converge. In other words, it diverges. This is going to help us out with so many really tough problems. Use this and you're going to be in such wonderful shape. Look at the follow-up, and this is equally valid and equally important. If the limit of the nth term does go to 0, frankly, we don't know if that series converges or diverges. Further investigation will be needed. Okay, so guys, we're going to take a look at this next example.